Hello viewers, my name is Dr. Ajay, Associate Professor from the Department of ECE, IARE, Engineering College, Hyderabad. Today we are going to discuss about the antenna arrays, that is 2-point sources with currents of equal magnitudes and with same phase. So today's topic is regarding arrays, that is antenna arrays, the basics of antenna arrays, and also let us study the 2-point sources with currents of equal magnitudes and with same phase. Let us start our session. So what is an array? Why we are going for an array? Let us take a general example, a simple dipole. Let us take a general example of a simple dipole. So we know that the radiation pattern, if it is vertically polarized, if the dipole antenna, it is vertically polarized, the electromagnetic waves will radiate in a horizontal direction in this way. So here you can observe here, there is only one single dipole. There is only single dipole. Let us say the radiation pattern, it is going into free space for a distance of 1 meter. For a distance of 1 meter. That means the dipole, here the dipole, the length of the dipole is 1 meter. The length of the dipole is 1 meter. And the radiation pattern or the electromagnetic waves are going to free space at a distance of, suppose let us say here 2 meters. So my requirement is we want to transmit the electromagnetic waves to farther distance. We want to transmit the electromagnetic waves to the farther distance. If we want to transmit the electromagnetic waves to the farther distance into free space, the only option we are having is we need to increase the length of the dipole antenna. That means we need to increase, that is from 1 meter to 2 meters. We need to increase the length of the dipole antenna from 1 meter to 2 meters so that the radiation efficiency into the free space increases to a distance of at least 5 meters. It may be around 5 meters. So like this, if we want to increase the radiation efficiency of the electromagnetic waves into the free space to 1 kilometer or 2 kilometers or 5 kilometers, we need to increase the length of the dipole antenna. That means if we want to transmit for longer distances around a range of 10 kilometers distance the electromagnetic rays, so we need to increase the distance, the height of the dipole antenna at least to 100 meters, at least to a length of 100 meters, so which is impractical. So we cannot design a dipole antenna with a distance whose length is 100 meters or 200 meters or 300 meters. Right? So the second option, there is another option we are having to increase the directivity. That means the directivity of the antenna is limited. It depends upon the length of the dipole. It depends upon the length of the dipole antenna and also the operating frequency range. If we want to increase the directivity of the antenna, we can place number of dipoles antenna in a regular fashion or adjacent to each other so that the directivity of the antenna can be increased. So the placing of antennas adjacent to each other in order to increase the directivity, we call it as an array. An array is nothing but it is a group of elements arranged in a particular order whose spacing will be same, whose spacing between the elements will be same. Here technically in our course antennas, waves and propagation, a single antenna can also be called as an element. A single antenna can also be called as an element of the antenna. So how many antennas we are using in an array, all those can be referred as the elements of the array. All those can be referred as the elements of the array. So best example for an array is, it is an Yagi-Uda antenna. So as we have seen in the earlier sessions, a Yagi-Uda antenna, it consists of a group of directors along with the dipole antenna, along with the reflector, and the number of directors may be from 2 and 40. So the maximum number of directors which we can use in an Yagi-Uda antenna is 40. So 2 and 40 is the number of directors. So as we increase the number of directors here, as we increase the number of directors, the directivity or the field strength produced by the array will be increased. That means we can propagate the electromagnetic rays to a further distance only by means of an array. That means you can see in an Yagi antenna, this is a dipole antenna, and here a reflector is placed here, and this is the dipole antenna here. So the length of the elements which we are going to place adjacent to the dipole antenna must be less than 2.5%. Must be less than 2.5% of the directors. So these are D1, D2, and D3 and D4. These are known as directors, or we can also simply call it as elements. We can also call it as elements of the array. So as we increase the number of elements, the directivity will be increased. So this is the main advantage of an array. This is the main advantage of an array. That means in order to increase the directivity and the field strength in the desired direction, a group of antennas are required to excite simultaneously. A group of antennas are required to excite simultaneously. Such a group of antennas is called as array of antennas or simply antenna array. So this is the one of the major application of an array, major advantage of an array. So only advantages of directivity and the field strength can be increased. So keeping in mind that in order to increase the directivity, the one of the basic specification to design an antenna array is the spacing must be uniform. The spacing must be uniform between the adjacent elements of an array, And also at the same time, whenever we are going to design an antenna array, see that the power fed to all the individual elements must be same. The amount of power that we are going to feed to each element of the array must be same, and at the same time the spacing between the elements must be same. So these are the two specifications basic required for designing an antenna array. Thus, antenna array can be defined as a system of similar antennas directed to get a required high directivity in the desired direction. So whichever the direction we want to propagate electromagnetic rays in one particular direction, so keeping in mind, depending upon our requirement, the directivity in one particular direction can be increased. Based upon this requirement, we can design an antenna with high directivity. Okay, it may be unidirectional, or we can also design a bidirectional antenna array. Let us take an example, Yagi antenna. So we have, when we design a Yagi antenna, this is a dipole antenna, and this is a reflector antenna, and this is a dipole antenna, and these are directors. D1, D2 and D3. So for this case, you can observe the directivity is unidirectional. The directivity of this Yagi, it is unidirectional like this. Right? So this is the best example to reach high directivity for an Yagi antenna. So for this case, you can say here, if this is a dipole antenna, the radiation pattern will be like this. And if at all you place one director, the radiation efficiency is increased to for the distance. And if at all you place two more directors here, if you place three more directors here, the radiation efficiency will be increased to a larger extent. That means more number of elements you place in an array, high directivity can be achieved in one particular direction or in the desired direction. So this is one of the basic advantage of the antenna array. So there are different definitions of antenna arrays. It is also known as a radiating system in which several antennas are spaced properly so as to get greater field strength at a far distance from the radiating system by combining radiations at points from all antennas in the system. It means that a single dipole antenna, suppose if you say this is an element, all these elements are connected. To a rod. This forms an array or antenna array. That means this is, suppose let us say this is dipole 1, this is one dipole, this is D2, this is D3, and this is D4, this is D5, and this is D6. So all these are dipoles which are arranged equally with equal spacing to a rod. When we apply some input signal to this rod or to this, when we activate these elements, some field strength is produced by the individual elements of the array. So the individual elements in our case are D1, D2, D3, D4, D5 and D6. So these are known as the individual elements. It means that each individual element will produce some field strength. Each individual element will produce some field strength. So that field strength may be E1. The field strength produced by the D1 will be E1. The field strength produced by the D2 will be E2. The field strength produced by the D3 will be E3. So like this, each of the elements in an array will produce some amount of field strength to some far distance. Now what is the total field strength produced by this antenna array? It means it is nothing but the vector sum of all the field strengths produced by all the elements of the array. It is nothing but the total field strength of the antenna array. That means E1 plus E2 plus E3 plus E4. It is nothing but the total field strength ET. So ET is equal to, ET refers to as total field strength produced by the antenna array. It is given by the vector sum of or the vector addition of the electric field strength produced by the individual elements of the array. That is E1 plus E2 plus E3 plus E4 plus E5 plus E6, and there will be some phase difference, and also there will be some phase difference produced by each of the individual element. Right? So every element of the array will be having some field strength and will be producing will be having some phase, and that means there will be some phase difference between the individual elements. There will be some phase difference between the individual elements, that is E1 and E2, or E2 and E3, or E3 and E4, or E5 and E6. So the phase differences generally we refer by the symbol psi. By the symbol psi. So ET is nothing but the vector sum of field strengths along with some phase difference between the elements. So antenna array, it is the radiating system in which the several antennas are spaced properly so as to get greater field strength at a far distance from the radiating system by combining radiations at point from all antennas in the system. In general, the total field produced by the antenna array at a far distance, it is the vector sum of fields produced by the individual antennas of the array. The individual element is generally called element of an antenna array. The individual element is generally called as element of an antenna array. So these are the basic, some basics of the antenna arrays. The antenna array is said to be linear if the elements of the antenna are equally spaced along a straight line. So this is a straight line, and if all the individual elements are spaced with equal spacing, the spacing is S1, the spacing is S2, the spacing is S3, the spacing is S4. If S1 is equal to S2 is equal to S3 is equal to S4, this is known as a spacing. If the spacing between the individual elements is same, that is S1 is equal to S2 is equal to S3 is equal to S4, and if all these elements are arranged along a straight line, then we call that array as an linear array. We call it array as linear array. And the linear antenna array is said to be an uniform linear array if all the elements are fed with a current of equal magnitude with progressive uniform phase shift along the line. With progressive uniform phase shift along the line. That means all these individual elements, let us say as individual elements as D1, D2, D3 and D4. The power fed to all the individual elements must be same. The power fed to all the individual elements must be same. And if there is a uniform progressive phase shift along the line, that means the phase difference between D1 and D2 is, let us say, as 5 degrees. Let us say between the D2 and D3, the phase difference is 10 degrees. Let us say the phase difference between the D3 and D4 elements is 15 degrees. Let us say the phase difference between D4 and D5 is 20 degrees. So you can observe here 5 degrees, 10, 15, 20. There is a difference of 5. There is a difference of 5 degrees of phase difference between all the individual elements of the antenna array. We can call it as a progressive phase shift. We can call it as a progressive uniform phase shift. Right? There is a progressive shift of 5 degrees and the uniform phase shift of 5 degrees here. Hence the name is given as progressive uniform phase shift. Hence the name is given as progressive uniform phase shift. That means there is a phase difference of increase in the phase difference at a rate of 5 degrees. At a rate of 5 degrees uniform phase shift along the line. Hence, whenever power fed to the elements of an antenna is same, to all the individual elements is same, And if there is a progressive uniform phase shift along the line, then we call it that array as a linear array. We call it that array as a linear array. In most of the cases, in any type of array, the antenna element in an antenna array, it is a lambda by 2 dipole. So in most of the practical applications that we are going to design, for most of the applications, in an array we generally take half wave dipole antenna, right? Half wave dipole antenna or half wave dipole elements. Half wave dipole elements. The length of the half wave dipole may not be equal to the electrical wavelength. The length of the half wave dipole will not be equal to the electrical wavelength, right? So the actual length, the physical length of the dipole antenna is not equivalent to the electrical wavelength of the dipole antenna. If the variation of the electrical length of half wave dipole antenna is 5%, then it is assumed that the radiation properties of individual elements are not affected. Right? If the variation of the electrical length of the dipole antenna is only 5%, then it is assumed that the radiation properties of individual elements are not affected. So various forms of antenna arrays. These are the different forms of antenna arrays we are having. One is a broadside array, end-fire array, collinear array, parasitic array. So these are the different forms of antenna arrays we can design. One is a broadside array, end-fire array, collinear array, and parasitic array. Let us see one by one what are these types of arrays: broadside array, end-fire array, collinear array, parasitic array. A broadside array, it is one in which a number of identical parallel antennas are set up along a line drawn perpendicular to their respective axes as shown in the figure. So in the broadside array, the individual elements are equally spaced along a line and each element is fed with a current of equal magnitude all in the same phase. That means you can observe in the figure here, all the elements are arranged parallel to each other. All the elements are arranged in a fashion parallel to each other, and these all elements are arranged perpendicular to a line or arranged to a line drawn perpendicular to the axis. This we call it as an axis, or this is a rod. Simply we can call it as a rod. All these identical elements with equal spacing are arranged perpendicular to the axis of the array, and at the same time the distance between the elements is treated as a small d, where d is same between all the elements. So for this design of a broadside array, the maximum radiation will be perpendicular. The maximum radiation will be perpendicular to the axis of the array. The maximum radiation will be perpendicular to the axis of the array. So such a design, we call it as a broadside array, where a number of identical elements are arranged parallel to each other, and all these are attached perpendicular to the rod or axis of the array, where the direction of maximum radiation will be perpendicular to the axis of the array. Such an array we call it as a broadside array. The end-fire array is nothing but a broadside array except that the individual elements are fed in or out of phase. Thus, in the end-fire array, a number of individual identical elements are equally spaced along a line, and individual elements are fed with currents of equal magnitude, but their phases varies progressively along the line in such a way to make the entire arrangement substantially unidirectional. It means the best example for end-fire array is Yagi antenna. The best example for an end-fire array is an Yagi antenna. That means all the individual elements are arranged in such a way that the radiation pattern, we want to direct the radiation pattern to one particular direction. So that means if we want to direct the radiation pattern to one particular direction, we need to design an antenna either by increasing the length of the elements or decreasing the length of the elements. That means all the field strength produced by the individual elements must be directed to the one direction. That means there must be some uniform progressive phase shift in one particular direction. Suppose if you design an Yagi antenna like this, this is an Yagi antenna. Here you can see there is a uniform progressive phase shift, and this design is made in such a way that the entire arrangement make the radiation pattern towards one direction only, right? So the individual elements are fed with currents of equal magnitude, but their phases varies progressively along the line in such a way to make the entire arrangement substantially unidirectional. That means we should design an antenna in such a way that all the radiation pattern will be either in this direction, or we can also design an antenna in such a way that the radiation pattern will be in this direction. Right? In such a way, you need to design an antenna by varying the length of the elements of the array. By varying the length of the elements of the array, you can direct all the electromagnetic energy to a particular direction. Such an arrangement, we call it as an end-fire array. Array. And there are two more collinear array. So collinear array, it is also an array where all the elements are arranged one over the other, or stacked one over the other. Such an arrangement we call it as the collinear array. Such an arrangement is known as a collinear array, where the individual elements are stacked one over the other, and this is the axis of the array, and the maximum radiation will be perpendicular to the axis of the array, and the maximum radiation will be perpendicular to the axis of the array. Such an arrangement we call it as a collinear array. And parasitic array. Say a parasitic array is one where only one element is given power, and all the elements will receive the power from the main element. That means, suppose this is best example is Yagi antenna. That means a dipole antenna, we are giving supply excitation, and all the reflector and directors are going to excite due to the dipole antenna. That means some amount of field strength is produced around this. Due to the amount of field strength produced by the dipole antenna, current is induced in this. Some amount of current is induced in the director D1. As the current is induced again around D1, some flux is generated, circulated around the director D1. Again, some amount of current is induced in the dipole D2. And similarly, as the current is induced into the D2, some amount of flux is circulated around the D2. Again, some current is induced in the director D3. So like this, we can see here, only the power is given only to the one element, and all the other elements get excited due to the power given to the element 1. All the other elements also receive some amount of current due to the dipole antenna, and hence this will radiate energy, and this will radiate energy. Right? So a parasitic array is nothing but the elements which depends on the other elements. The elements which depend on the other element. Right? So we call it as a parasitic array. That means the reflector and the directors are depending upon the main dipole antenna. This reflector and the directors are going to receive the electromagnetic energy from the dipole antenna, and they also get excited. So such an arrangement we call it as a parasitic array. So the main difference between the parasitic array and end-fire array, you can see here, the end-fire array and the parasitic array both are unidirectional. And the broadside array, it is a bidirectional, and this is a collinear array, it is also bidirectional, and this is unidirectional, and this is unidirectional. And here, in this, all the elements are given power supply. You can see here in the end-fire array, all the elements are equally spaced, all the elements are identical, and the arrangement is made in such a way that the radiation pattern will be directed towards one particular direction, Here also the same thing, the parasitic array also. The only thing is, here we are going to give power only to one element. Here all the elements are given power. The directivity will be unidirectional in the end-fire array. In the parasitic array, it is also unidirectional. So this is one of the major difference between the end-fire array and the parasitic array. And moreover, in end-fire array, as we are giving power to all the elements of an array, the field strength produced in an N5 array case will be more than the parasitic array. In the N5 array, the field strength produced will be more than the parasitic array, which are unidirectional. The array of point sources is nothing but the array of an isotropic radiators occupying zero volume. So let us see how to draw the radiation pattern by taking 2 point sources into consideration. Suppose before going to n number of elements, before going to design an array of n number of elements, let us take for an example an array which consists of only 2 elements. So if there are 2 elements, it is also known as an array. When there are 2 elements, it is also known as an array. The array of point sources is nothing but the array of an isotropic radiators occupying zero volume. So for greater number of point sources in the array, the analysis of the antenna array becomes complicated and time consuming. Right? If there are more number of sources are there in an array, the mathematical analysis of the antenna array becomes complicated and it will be time taking. So let us take a general example for simplification of mathematical analysis. Only 2 point sources in an array. Also, the simplest condition of point sources is in the array is 2. The simplest condition of point sources in the array is 2. Then conveniently, analysis is done by considering 2 point sources which are separated by distance d and having same polarization. Right? So let us, for our convenience, to reduce the complexity of mathematical analysis of array, let us take 2 point sources are separated by small distance d, having the same polarization. That means 2 point sources are having same polarization. That means the field strength produced will be similar. The field strength produced by 2 elements will be same. It may be either circular, it may be or elliptical, or it may be linear. So see that the point sources which we are going to take for our design of mathematical analysis, let us take 2 point sources of equal polarization. Let us assume the distance between the 2 point sources is small d. And whatever the mathematical design we are going to do for 2 point sources, this can be extended for n number of point sources. in the array. Let us discuss about an array of 2 point isotropic sources with a distance of separation d between them. So an isotropic source, it is nothing but which radiates uniformly in all directions. We call it as an isotropic point source with a distance of separation d between them. The polarization of 2 isotropic point sources is assumed to be the same. The polarization of 2 isotropic point sources is assumed to be the same. To derive expressions, following conditions can be applied to the antenna array. So there are 3 cases. Let us say, for example, 2 point sources with currents of equal magnitudes and with same phase. Right? So let us consider 2 point sources 1 and 2. Both are given equal supply, that is equal magnitude and same phase. Same phase means there will be same phase of for individual elements of point sources in an array. And the second case is 2 point sources of equal magnitudes but with opposite phase. And 2 point sources with currents of unequal magnitudes and with opposite phase. Let us see these 3 different cases. So the radiation pattern of 2 point sources with currents of equal magnitudes and with same phase, with currents of equal magnitudes but with opposite phase, 2 point sources with currents of unequal magnitudes and with opposite phase. Let us see the first case first. So 2 point sources with currents of equal magnitudes and with same phase. So whenever we want to find out the field strength produced by these 2 point sources, so we should know that every point source will produce some amount of field strength. What is the amount of field strength produced by the point source 1? And what is the amount of field strength produced by the point source 2? And the summation of a field strength produced by the points 1 and 2 gives the total field strength produced by the point sources which are arranged in the form of an array. Let us assume here in this diagram 1 and 2, that is the point source 1 and the point source 2 are separated by a distance of d, and these 1 and 2 are placed midway at the center of the origin. Let us say O as the origin. Let us say O as the origin, and these 1 and 2 point sources, exactly the midpoint of these 2 point sources is placed at the origin of the axis. Let us say as O. Let us say as O. Let us assume here there is a P. P is the great distant point. That means some amount of field strength is radiated by these 2 point sources 1 and 2. 1 and 2. So obviously we can see that the field strength produced by the point source 1 will reach to the distant point P at a later time than point source 2. Right? So you can see here the distance between the 2 and P is very less. The distance between the 2 and P is very less, and the distance between 1 and P is more. The distance between 1 and P is more here. That means there is some difference of distances between 2 and P, and also there is a difference of distance between 1 and P. Between 1 and P it is very large, between 2 and P the distance is very less. So due to these differences in the distance, so we can observe clearly that the field strength produced by the point source 2 will reach to the point P in a small amount of time than the field strength produced by the point source 1 to the point P. So we can say that the electromagnetic rays from source 1 reaches the point P at a later time than the waves from the source 2 because of the path difference. That means there is some gap, there is some distance, increase of distance and decrease of distance between the 1 and P and the 2 and P. So we call this a difference of distance. We call it as a path difference 1 dash 2 dash. We call this as a path difference 1 dash 2 dash involved between the two waves. Thus the fields due to the source 1 lags while due to the source 2 leads. That means the electromagnetic waves produced by the 2 will lead here. That means they are coming at a faster rate they are going to reach the distant point P within a small amount of time. That means the fields produced will be leading. Here the fields produced will be lagging. They are going to reach point P with some delay. They are going to reach the distant point P with some delay. Let us also consider this delay. That is, let us also consider this delay, which indirectly we can say this is a path difference involved between the two phases. As there is a path difference between the two waves, there will be some phase difference between the 1 and 2. Right? So there is due to the path difference between the point sources 1 and 2, there is some phase difference between the 1 and 2. So I can observe in the figure, D is the distance here. You can see here, it is the center. It is a distance between the 1 and 2. So as we have seen, O is the center between 1 and 2. The distance between O and 2 is D by 2. And the distance between 1 and O is the D by 2. Let us draw a line parallel from O. Let us draw a line parallel from 2 to a distant point P. Also draw a line parallel from O to a distant point P. Also you draw a line parallel from the point 1 which is parallel to the 1 dash and 2 dash, which is to the 1 dash and 2 dash. Let us assume this angle as theta. Here, and here this is a 90 here. This is 90 here. Now we can say here, if we consider this as a cos theta, right? What is this cos theta? Let us consider triangle O, 2 and 2 dash. Let us consider this triangle O, 2 and 2 dash. So if we draw this triangle here separately, you can see here we draw this triangle separately. So O2 and 2 dash. So O2 and from this triangle is taken. You can observe here O2 and 2 dash. So 2 dash there is theta. 2 dash here. So cos theta is equal to So cos theta is equal to adjacent side to theta. So this is adjacent side to theta. So cos theta is equal to O2 dash by O2. Right? So cos theta we can write as O2 dash by O2. You can see here cos theta is equal to O2 dash by O2. Now what is the distance of O2 dash? So O2 dash is equal to O2 into cos theta. Now what is the O2? D by 2 cos theta. So O2 dash, this distance is nothing but D by 2 cos theta. This distance is D by 2 cos theta. And at the same time, if we apply here also, if this is 90 degrees, we can take here as cos theta. So we will get here D by 2 cos theta. So here 1 dash theta, 1 dash O and 2 dash O is equal to D by 2 cos theta. Right? So 1 dash O and O2 dash. So 1 dash O and O2 dash are same distance, that is D by 2 cos theta. So this is the path difference. So 1 dash 2 dash is the path difference. So what is the total path difference? So D by 2 cos theta plus D by 2 cos theta. So D by 2 cos theta plus D by 2 cos theta is equal to D cos theta. Is equal to D cos theta. So this is the path difference between the point sources 1 and 2. Between the point sources 1 and 2. So here we have determined first the path difference. Now what will be the phase difference? What will be the phase difference between these two point sources? If we want to, let us assume here the phase difference between the 2 point sources has by the symbol psi. So psi is equal to path difference into 2 pi by lambda. So that is in a electromagnetic wave theory, we have seen that the phase difference, it is nothing but the path difference multiplied by 2 pi by lambda. Now what is the path difference here? 1 dash 2 dash. 1 dash 2 dash into 2 pi by lambda. What is 1 dash 2 dash? So 1 dash O plus O 2 dash into 2 pi by lambda. So 1 dash O plus O 2 dash is equal to D cos theta. So D cos theta into 2 pi by lambda. So this 2 pi by lambda can be written as beta. So we can write it as beta D cos theta. So 2 pi by lambda is nothing but beta plus the propagation constant. We can label it as beta D cos theta. Right? So simply psi is equal to beta D cos theta, which is the phase difference between the 2 point sources. Psi is equal to beta D cos theta, which is the phase difference such that these are given equal magnitude and are in same phase. See here, you can see here the path difference is D by 2 cos theta plus D by 2 cos theta meters, which you can note it as D cos theta meters. And the phase angle psi is equal to 2 pi by lambda, 2 pi by lambda into path difference, 2 pi by lambda into path difference. So we can write it as 2 pi by lambda into D cos theta, and psi is equal to beta D cos theta radians. Psi is equal to beta D cos theta radians. So we need to remember this equation for the entire antenna arrays where the phase difference is beta D cos theta. Let us assume here as E1 is equal to far electric field at distance point P, and E2 is the far electric field at distance point P due to source 2. E is the total electric field at distant point, and psi is equal to beta D cos theta radians. So here there are two elements 1 and 2. The field strength produced by 1 is considered as E1. The field strength produced by point source 2 is considered as E2. And the total far field at distance point P in the direction of theta, it is given by E is equal to E1 into E power minus j psi by 2 plus E2 into E power j psi by 2. So generally any wave equation we name it as E power j psi. Any wave equation we can specify it as a E power j psi. That means here the waves are getting from point source 1 and point source 2. Hence we are dividing this E power j psi as j psi by 2 for one point source and E power j psi by 2 for another point source. As one is leading, that means the waves produced by one point source is leading. The other point source, the waves produced will be lagging. You can observe here this is lagging here and this is leading here. Leading means positive, lagging means minus. That means the waves produced by point source 1 we can indicate as E power minus j psi by 2, As this is leading in the point source 2, we can write it as e power j psi by 2, positive sign. So whenever lagging is there, we can take minus symbol e power minus j psi by 2. As this point source 2, the waves produced are leading, we can call it as e power j psi by 2. The total summation of the waves produced by point source 1 and 2, the total field distance is nothing but e power j psi by 2 plus e power minus j psi by 2. So this is the total field strength produced by the 2 point sources, where E1 indicates the far field electric field of one point source, E2 represents the electric field strength produced by the point source 2, and this is lagging, minus symbol indicates this is leading. Let us do the summation of, let us apply some trigonometric formula here. Is equal to 2 E naught into e power minus j psi by 2 plus e power j psi by 2. If you dividing by 2, you multiply by 2 here, divide by 2, multiply by 2, you will get 2 E naught into e power minus j psi by 2 plus e power j psi by 2 by 2. So we know that from the trigonometric series, cos theta is equal to e power j theta plus e power minus j theta by 2. So applying this trigonometric series to the above equation, we get cos I by 2. Right? So cos x plus cos theta. So cos theta is equal to e power j theta plus e power minus j theta by 2. You get simply as 2 E naught is equal to cos I by 2. So we know that psi is equal to beta d cos theta. We know that psi is equal to beta d cos theta. You substitute this psi value here. Substitute this psi value here. You will get totally E is equal to the total field strength is equal to 2 E naught into cos of beta d cos theta by 2, where this 2 E naught represents amplitude and this cos function represents the phase produced by the 2 point sources of the array. If we assume 2 E naught, if we want to normalize the electric field pattern, let us assume 2 E naught is equal to 1. If 2 E naught is equal to 1, the remaining terms will be cos of beta d cos theta. Now let us assume d, the distance between the separation between the two elements as lambda by 2. That means between element 1 and between element 2, the spacing is d. Let us assume this as lambda by 2. If d is equal to lambda by 2, if we substitute beta is equal to 2 pi by lambda here and d is equal to lambda by 2, if we simplify, the total electric field given by the 2 point sources, if they are separated by distance of lambda by 2, it is given by E is equal to cos of pi by 2 cos theta. Right? So the 2 point sources of equal amplitude and phase, whose sources are separated by distance of lambda by 2, the total field strength produced in this case will be cos of pi by 2 cos theta. If we want to draw the radiation pattern for these 2 point sources, we need to consider the maximum point and the minimum point and the half power point distribution. That means half power point distribution or the half power beamwidth angles. We need to know in which direction the radiation pattern is maximum and in which direction the radiation pattern is minimum from these 2 point sources. Let us take the function to find out the maximum direction. So E is maximum when cos of pi by 2 cos theta is maximum. And we know that the maximum value of cos is plus or minus 1. So under this consideration, cos of pi by 2 cos theta, that means this is E. E is maximum when cos of pi by 2 cos theta is maximum. And when we know that cos function is maximum, when its maximum value reaches is plus or minus 1. So under this condition, cos of pi by 2 cos theta is equal to plus or minus 1. And if we apply the trigonometric solution for this equation, pi by 2 cos theta max will be equal to plus or minus n pi. As we are going to find out the maximum value, we have named it as theta max. As we are going to find out the maximum direction value, theta can be specified as theta max. The trigonometric solution for this function is, this is the solution from the trigonometric series, plus or minus n pi. If suppose n is equal to 0, you will get pi by 2 cos theta max equal to 0 and cos theta max equal to 0. So the solutions for this theta max will be 90 and 270. So theta max is equal to 90 and 270. That means the maximum direction will be in the direction of 90 and 270. The maximum direction of radiation pattern will be in the direction of 90 and 270. And similarly, the minimum value you can find out, cos of pi by 2 cos theta will be minimum. The minimum value is 0. If cos of pi by 2 cos theta is equal to 0, or we can specify this theta as theta min here. The trigonometric solution given for this function is plus or minus 2n plus 1 into pi by 2. If n is equal to 0, consider n is equal to 0, pi by 2 cos theta min is equal to pi by 2 and cos theta min is equal to plus or minus 1. So theta min will be 0 and 180. theta min will be 0 and 180. That means the minimum values, the maximum is 90, 270 and minimum is 0 and 180. So maximum radiation pattern we know, and the minimum radiation pattern in which direction we know. Now let us find out the half power point direction. So similarly, as we have simplified in the above case, let us take E value. E is equal to cos of pi by 2 cos theta. It will be maximum at the rate of half power points, which we know that plus or minus 1 by root 2. The proper trigonometric solution for this is given by plus or minus 2n plus 1 into pi by 4. That is, at half power points, the maximum value of voltage will be plus or minus 1 by root 2. The solution, trigonometric solution, it is given by plus or minus 2n plus 1 into pi by 4. Suppose if you substitute n is equal to 0 here, you will get only pi by 4. You will get only pi by 4. If you simplify, cos theta HP PD is equal to plus or minus 1 by 2 and theta HP BD is equal to 60, 180. So the maximum is 90 and 270 and the minimum is 0, 180 and these are the half power point direction. So for all the cases, we need to determine the maximum direction, minimum direction and half power point direction, whether it may be broadside array, it may be end-fire array or collinear array or unequal amplitude or unequal spacing. So to determine the radiation pattern, these are the prerequisites. These are the prerequisites to draw the radiation pattern for any case of the antenna array. So for this case, you can write here 90 and 270. You can see here. So here for this, we know that we draw a 0. This is 90. This is 180 and this is 270. So maximum 90 and 270. So this is maximum. Minimum is 0 and 180. These are nulls here. Minimum. And half power point are 60, 120. So this is 60 and this is 120. So these are 60 and this is 120. This is 60 and this is 120. So this is the final radiation pattern of 2 point sources with equal amplitude and spacing, separated by distance of d is equal to lambda by 2. Right. So in order to draw the radiation pattern, so we need to determine the total electric field strength produced by the antenna array. From that equation E, you need to determine the maximum radiation pattern and the minimum radiation pattern and also the half power point distribution. So based upon these three specifications, after finding out through mathematical analysis, we determine first E, we determine max radiation pattern, we determine minimum, and we determine HP, half power point radiation. So based upon these four, we need to draw the final radiation pattern, which is, you can see here clearly. These are 2 point sources 1 and 2 separated by distance. So if these 2 point sources are separated by distance of d is equal to lambda by 2 and power is fed is equal magnitude and the spacing is lambda by 2, the maximum amount of direction will be 90 and 270 and the minimum will be 0 and 180 and these are the half power point 60 and 120 degrees. So this is the final thing of the array of point sources of equal magnitude and spacing. Let us discuss about the arrays of 2 point sources of unequal amplitude and spacing, equal spacing in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.